Assalamualaikum warahmatullahi wabarakatuh and hi. For this group assignment video for the subject Modern Algebra MKG3013, we will be talking about Cayley table. Now let's get started. This is our team members. First, Farah Quraisha, Puve Nayata anak perempuan Sibak Kumar, Nur Suhada binti Muhammad Rozi, and Siti Nur Syafika binti Kadir. This is the contents of our topic. First, the introduction, properties of Cayley table, examples of Cayley table. Now let's get started with the introduction. A Cayley table after the 19th century British mathematician Arthur Cayley described the structure of a finite group by arranging all the possible product of all the group's elements in a square table reminiscent of an addition or multiplication table. Many properties of a group, such as whether or not it is abelian, which element are inverse of which element, and the size and contents of the group center can be discovered from its Cayley table.
The property of Cayley tables. The first one is commutativity. The Cayley table tells us whether a group is abelian because the group operation of an abelian group is commutative. A group is abelian if and only if its Cayley table's value are symmetric along its diagonal axis. The group 1 and negative 1 above and the cyclic of order 3 under ordinary multiplication are both examples of abelian group, and inspection of the symmetry of the Cayley tables verify this. In contrast, the smallest non-abelian group, the dihedral group of order 6, does not have symmetry Cayley table. The second one is associativity. Because associativity is taken as an axiom when dealing with group, it is often taken for granted when dealing with Cayley tables. However, Cayley tables can also be used to characterize the operation of a quasi-group, which does not assume associativity as an axiom. Unfortunately, it is generally possible to determine whether or not an operation is associative simply by glancing at the Cayley tables as it is with commutativity. This is because associativity depends on a three-term equation, while the Cayley table shows two-term products. However, like associativity tests can determine associativity with less effort than brute force. And the last one is permutation. Because the cancellation property holds for groups, no row or column of a Cayley table may contain the same element twice. Thus, each row and column of the table is a permutation of all elements in the group. This clearly restricts which Cayley table could conceivably define a valid group operation. To see why a row or column contain the same element more than one, then let's A, X, and Y be the element of a group with X and Y distinct. Then in the row representing the element A, the column corresponding to Y contain the product AX. Similarly, the column corresponding to Y contain the product AY. If the two products were equal, that is to say, rows are contain the same element twice, our hypothesis that AX will equal to AY. But because the cancellation law holds, we can conclude that if AX equal AY, then X equal Y. It is a contradiction. Therefore, our hypothesis is incorrect. A row cannot contain the same element twice. Exactly the same argument suffice to prove the column case. And so, we conclude that each row and column contains no element more than once because the group is finite. The pigeonhole principle guarantees that each element of the group will be represented in each row and in each column exactly once.
As for the Cayley's table, there are two examples. One is multiplication, another one is addition. I'll walk through with the multiplication one. So for the multiplication, you can see there is an example that when we are doing multiplication by using the Cayley's tables, we have to make sure that we know the table rule, like 1 times 1 1, 1 times 2 2. As you can see the table in the down part, we have to follow that one. That one is the basic one. So the Cayley's table is convenient to check the commutativity, which is the property of the Cayley's table. As for the Cayley's table, first we have to know the history, right? So Cayley's table, or the group multiplication table, founder is Arthur Cayley. That's why the table's name is Cayley's table. And for the example, we can straight away walk through the example. For the group, let's say we are taking the group operation, which is the times, and 1, -1, I, and -I. That's the example that I give. First off, we have to put our group operation on the top left over there, so there is a times over there. And then for the header, for the column and for the row, for the column and for the row also, we have to put 1, -1, I, and -I, and then follow that one. So 1 times 1, 1, -1 times -1 is 1. You can see I times I is -1, and -I times -I is -1. And also this is called the features of Cayley's table. And of course you can see that the first starting on the the vertical side, right, you can see 1, -1, I, and -I. And this side same, 1, -1, I, -1. You can say that the same the row and the column is following the header, so we must follow that one. And also every column contains identity elements, like each row and each column has that number 1. So this one also have number 1. You can see the second also number 1, and the third row and the last part also number 1, and the fourth one also have number 1. So because in a group every element has an inverse. Okay, this table is symmetric and it's about diagonal, and so this group is called abelian. So abelian means A times B equals to B times A. That's what we call. Let's go to the non-abelian group. So for the non-abelian group, the multiplication table is non-symmetrical. So when it's not symmetrical, there is no duplicate elements in rows and columns. Like just now I said, right, we don't have that each row and each column don't have the number 1. The first, as for the abelian group, they have, but for the non-abelian group, we don't have. See the example that I've given. There is row with duplicate elements and there is a column with duplicate elements. There won't be a contraction between them. So when there is no contraction, we can confidently know there is no symmetrical. So with that, we can know it's non-abelian group with no symmetrical, and we won't follow the inverse one, the inverse rule, right? So as I can say, the Cayley's table is convenient to check commutativity of the operation, and cancellation property, symmetrical relativity to the diagonal properties. Left cancellation holds if each row contains all elements. Right cancellation holds if each column contains all elements. Existence of the identity element and existence of the inverse. We have to know the property before we are doing the multiplication, and so we have to know whether that one is an abelian group or a non-abelian group. Then only we can know whether that one is symmetrical or non-symmetrical, so that we can do according to their property of the Cayley's table.
Okay, now let's find all group of order 3. We call the 3 elements E, A, and B, where E is an identity elements. Because E is the identity element, we can quickly fill in the first row and first column. This leave 4 empty square in our Cayley table. So let's try to riddle out what goes in this square. So for the second column and second row, it can be A because this row already contain A. This means it's either E or B. So let's guess E and see what happened. If A times A equal to E, the final square in the second row must be B. This is because each row and column has to contain all elements, but the moment we write B, we see the problem. The third column now contains 2 B's. This is not allowed. Our guess is wrong. So A times A must be equal to B. We can now fill the rest of the table since we have already used A and B in the row 2. Last square must be E. Okay, similarly, since there is already an A and B in the second column, this empty square must also be E. And lastly, the third row already has a B and E, so B times B equals to A. So there is only one group of 3 in this Kylie table because this table is symmetric about the diagonal and it's an abelian group. This group is identical to integer mode 3 under addition. We say that they are isomorphic groups. Here's one way to see this. Let's compare this table to the Kylie table for the integer mode 3. If you were to replace E with a 0, A with 1, and B with 2, the two tables would be the same. Okay, by the way, you may have noted that filling in Kylie table is kind of like solving a Sudoku puzzles. Each row and each column must contain all the elements of the group and there can be no duplicate elements.